Hi, this is Dr. Lesher, and this video corresponds with Chapter 4, Section 1. It's all about chemical reactions, and you're a little familiar with chemical reactions. You've seen some in class and demos, and one thing that you've learned about them is that bonds change. Chemical bonds change. They may be broken and reformed, and the identities of the chemicals are different before and after the reaction. So we can say that reactants, what we start with, are consumed and new products are formed. So in our reactions, we list all those participants and their relative molar amounts. Often we put in the state of matter, solid, liquid, gas, or aqueous solution, meaning dissolved in water. And we start with the reactants on the left and the products appear on the right. You can't really see this sort of molar ratio when you're doing a reaction. If you were in a factory making ammonia gas, you start out with nitrogen gas and hydrogen gas. They'd probably be in cylinders of some sort, and when they're combined together, they form ammonia gas. You don't really see this balanced chemical reaction, but it's important because it dictates how much of that product is going to be made and how much of the reactants are going to be used. It's like a recipe. That ammonia gas that might be generated through this process, which is called the Haber reaction, is then mixed in water to form the ammonia like cleaning solution that you can just buy at Walgreens. But let's think about sort of the molecular scale. So nitrogen and hydrogen are both diatomic molecules. They're part of that set of elements in the I have no bright and clever friends mnemonic, where when you've just got them by themselves, and you can see in the way it's written on these gas cylinders, there's two atoms attached together. Ammonia is a molecule that has one nitrogen and three hydrogens. So one thing that's pretty apparent is that we don't have the same number of atoms if we just are looking at one molecule of each thing. For example, with the hydrogen, the diatomic molecule has two hydrogens, but the ammonia molecule has three. So we need a ratio other than 1:1 to combine these gases in to make the ammonia gas. So the way that it would work out at this atomic level is that you're going to need three hydrogen molecules and one nitrogen molecule to form two ammonia molecules. This is the only ratio that's going to work, and you can't have atoms left over, you can't have atoms unused. So this is the only way that this reaction is going to work. We can see that it's balanced on both sides. The same number of atoms are on the reactant side and the product side. So a few characteristics of balanced chemical equations. As I just mentioned, the number of atoms are the same on the reactant side and the product side. The reaction proceeds from left to right, so we start with the reactants on the left. And you also saw in that last example some integers. We call these coefficients or stoichiometric coefficients. And if there's no number shown, then it's assumed to be a 1. But these stoichiometric coefficients are very important, and they're showing the molar ratio of how the reactants are combining and in what ratio products are formed. That ratio has to be the simplest ratio, so the smallest integer. And then also charge is conserved. And so if we have ions in the chemical reaction, charge is also conserved. So a little more on those coefficients. Those coefficients represent, at the atomic level, the relative numbers of molecules. So with that ammonia reaction, one nitrogen molecule for three hydrogens. But when we scale it up to amounts that we can actually work with in the lab or the factory, since moles are just a number of molecules, those coefficients are also indicating the relative numbers of moles of reactants. So with that ammonia, we could say that 1 mole of nitrogen molecules reacts with 3 moles of hydrogen to produce 2 moles of ammonia. So let's start with a new reaction now and balance it. So in this reaction, I have an alkane, so carbons that are singly bonded. There's 3 of them, so what would that be? It would be propane. Got propane reacting with oxygen, forming the products carbon dioxide and water. And just by looking at the numbers and colors of the atoms on the left and the right, we can see that we're not balanced. So that carbon, since I have 3 on the reactant side, I'm going to need to form 3 CO2 molecules. So I can adjust coefficients to create this balance. So if I have 3 carbon dioxides, that now kind of changes my numbers of oxygens. And a good thing to do is to kind of make a little tally. So if I have carbon, hydrogen, and oxygen, I started out with 3 carbons on the left, 8 hydrogens on the left, and 2 oxygens on the left. And on the product side over here, I started out with just 1 carbon, 3 oxygens, and just 2 hydrogens. And by changing the coefficient here to a 3, I now have 3 carbons. Now that also changes my number of oxygens, right? If I had 3 of these CO2 molecules, I'd have 6 oxygens here plus the 7th over on the right side. What else is out of balance here? The hydrogens are also out of balance. I have 8 hydrogens on this molecule. I only have 2 here. So that means I'm going to have 4 of those water molecules. Now this is going to give me 8 hydrogens, which is good, and it's going to further change my oxygen number. Now I've got 4 oxygens here and 6 here, so that changes it to 10. Can you guess what our last step is here? We need to have 10 oxygens on the left side, so I would need a coefficient of 5 on the oxygen, and that would bring me to 10. So when you really draw it out like this, you can see it just kind of makes sense that this is the ratio at which propane and oxygen react, and this is the ratio at which those products are formed. So a few more tips. It's good to balance just one element at a time. It's often good to save oxygen and hydrogen for last. Do not change the subscripts in the compound chemical formulas. Those subscripts in the compound's formula are indicating what compound it is, and we can't just change that because then we would have a different reaction. When you see polyatomic ions, usually they stay the same on the reactant and product side of the equation. And then at the end, just double check everything. See if there's the same number of atoms of each element on the reactant and product side. So here's one for you to practice with. I again encourage you to make that little tally, so you can count up your nitrogens, count up your hydrogens, count up your oxygens on each side of the reaction, and then try to balance it. So I'll let you work on that one on your own, and I hope you found this helpful.